When you're using the system, it shuts off what the motor normally did and it takes over. So it's a different power system and not a power adder.
So what's the big deal with compressed air?
There is no energy consumed, or there are no parasitic losses from the vehicle with compressed air supercharging. The amount of energy or power it takes to compress the air is all done with the tanks outside of the car. So essentially you're getting something for nothing, as opposed to, again, with a supercharger, you've got the parasitic mechanical losses coming straight off the drive of the snout of the crank or whatever, and the efficiency of the blower. And with a turbocharger, you're using exhaust energy, but you're creating back pressure in the system, which decreases the amount of airflow through it. So I mean, you don't get something for nothing with any of those power adders. With this, you do.
Compared to nitrous, then?
Nitrous is dangerous stuff.
Is it?
Hello.
The day job, I work with compressed natural gas, liquid natural gas, propane, and hydrogen in fuel delivery and fuel management systems for industrial engines and some over-the-road stuff in Asia. So between that and the time at NOS, I worked on gaseous fuels, pneumatic stuff for 27 years. And my schooling or education was aerospace engineering, focusing on fluid mechanics. This dual system should be capable of 2,000 horsepower, give or take, maybe a little more, I don't know. So I'm not going to be driving anything with that kind of power in it, so it's going to have to go in someone else's car.
I might have to drive it.
When you look at it, as you run high loads of nitrous oxide, peak cylinder pressure walks all over the place, and so you end up retarding timing to accommodate for the unstable combustion. You're sacrificing efficiency to keep from breaking the motor with nitrous by retarding the timing. That's really what it comes down to, because a significant amount of the energy that occurs with nitrous is from the release or the disassociation from the nitrogen from the oxygen. It's not that, oh, we're burning a whole lot more fuel, blah, 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 blah. It really, if you get into the physics of combustion, only a small percentage of the gain is due to the actual increased fuel you burn. A huge amount is the energy release of the nitrous coming apart. And this is a much more normal combustion because it's just air, but you can force as much air as you want to into the engine, and that's one thing that people have a very hard time getting their head around with this, is this system doesn't care what size engine you put it on. It'll flow the same amount of air on a 500 cubic inch engine as it will on a 2-liter. Nitrous, you end up throwing extra fuel at it to try to keep combustion temperatures down, to absorb that heat, so to mitigate that abnormal combustion. So you end up running much richer mixtures with nitrous than you do with this. This thing will run anywhere from, it doesn't care, 12 to 1 to 13 and a half to 1, and make the same power.
How about that?
Yeah, it's true. All of it.
Once more, it doesn't care what size engine you have. It'll flow the same amount of air on a 2-liter as it will on a 10, 12-liter. You'll run more boost to do that, but given the physics of the system, it doesn't care. So we could put this thing may make 900 on this. We could put it on a 2-liter and just turn the boost up to whatever, 20 pounds, and the system will still make 900 horsepower. Because the engine is, as you were saying, the engine's just a big air pump. It's just a big restriction to this. This is forcing air through it. The bigger the engine, the lower the restriction. The limits on the flow capability are in the system, not in the engine. That's very different from a supercharger or a turbo or anything else.
Well, we designed our test car to be as simple as possible. It's very much like driving a normal car. We have ignition and we have fuel pumps. The driver simply starts it, stages it, and the system comes on electronically and away you go.
When fully charged, these are at about 3,300 psi or 220 bar. And the valves are size, so for the flow rates that we are targeting for this system, you can make full power all the way down till they're down to about 300 psi. So that's why they're very special valves. They're very, very high flow valves. There's nothing industrial like these out there. We had to design these for a purpose. So anyway, we start at 3,300. We feed into this, which is a single stage mechanical regulator, piston style balanced. So it's set for 120 psi outlet pressure. So from a balanced regulator, it means the outlet pressure is the same regardless of what the inlet pressure is. So whether these are at 3,300 or they're almost empty down to 300, the outlet pressure is the same. It's still 120 psi. This is the high pressure side of the system from here to here. Outside of that, everything down here is relatively low in the 120 range. So anyway, it's a -20 SAE line that runs to the front of the car. Those two bottles in this car, well, those two cylinders hold about 300 standard cubic feet, and we use 1 1/4 cylinders per run. So we use about 60% of those. So literally those have to be charged every run. 1 is not quite enough, 2 is more than you need, but you know, you have a limited selection or availability on those things.
And then you use regular tubes to fill.
No, you just fill it with like a scuba air compressor. Okay. Feed hose from the mechanical regulator runs through the car up here to the safety shutoff valve. It is an electromechanical shutoff valve. You can think of it somewhat similar to a nitrous solenoid, only much, much bigger. The orifice in this is 1.5 inches in diameter. It functions somewhat analogous to a nitrous system. You arm it, you open the bottle valve, that pressurizes everything up to here. When the system is engaged or becomes operational, the safety shutoff valve snaps open, air starts flowing from the line through the butterfly valve, and the butterfly valve is moved or articulated to maintain boost in the intake manifold via the boost controller. The air, as it passes through the butterfly valve, is then injected into or through the device we call the ejector into the engine inlet tract. This device also features a mechanical butterfly valve that is slammed shut once the engine comes up on boost, so that the engine is running solely off the compressed air in the back of the vehicle, and will continue to do so until such time as the driver comes off the throttle or the air supply is exhausted. Then it will snap back open and the engine goes back to running normally aspirated.
You said earlier there's no timing change or...
Correct. The engine configurations we've used to date, there's been no change in fuel quality required or in engine tune, including engine timing, from what the engine uses normally aspirated. The main reason for this system to exist is its an ability to pressurize, supercharge an engine without incurring any parasitic losses. And in addition to that, charged air temperatures are dramatically low.
So this is how we started testing with the EFI. We used it because we could control the amount of fuel that was going in the motor, and with the map sensor we could get our computer controller to follow the fuel flow with air pressure, and it enabled us to get our R&D done. Once we did that, we now had the opportunity to put a carburetor on. And it's a special carburetor that's modified to blow air through, and it gives the correct amount of fuel to air ratio, and it follows it beautifully. So it's come about, I would say, in the last 10 years, because when we started testing, there wasn't really something that was consistent enough, and now they make good blow-through carburetors, and we were able to, prove that by testing. But we had to start with EFI because we had a known amount of fuel and a known amount of air, and we had to get them coordinated together before we could go to the carburetor.
So how much horsepower do you make?
The engine on its own will make 400, a little bit more horsepower. It's a 350 Chevy, 6,000 RPM motor, 9-to-1 compression, hydraulic roller. With 8 pounds of boost or so, it's over 800 horsepower. It makes about 50 horsepower for every pound of boost.
So when and where can I buy it? What? He will never sell it.
We'll never sell cars. Take it for free.
We have the computers, were finished late in 2016. We proved them out during our testing. So in 2017, we plan to be able to have some customers running our system. And we're very excited to be able to market it after so many years of research and development.
When did you start?
We started in 2002, and we started with a system that was very similar to what we have now, but it took testing and there was many things that we had to improve to make them work with the very cold temperatures, and certain things had to be changed, and the computer had to be built, and everything that we're using now had to be made for our system. It wasn't anything off the shelf that we could use, so it's been a long haul.
But it was good that you had a rocket guy aboard.
Yeah, Rocket Karl, thankfully. He never gives up.
His wife wishes he would.
What was the most difficult part? Or are you in it now?
Yes. It's a normal development cycle. You come up with an idea, you design it, you build it, and you find out what works and what doesn't. Those valves on the cylinders, we've got, 3-4 years figuring out how to make those work correctly, because no one had ever done anything like that. That safety shutoff valve I showed you, the concept is somewhat similar to industrial valves, but they're big and they're slow and they don't flow enough. This thing has to react quick enough it'll work on a race car.
But did you visualize the goal? Did you know it was possible? Or?
Well, yeah, physically possible. You can draw this on the back of a napkin in 5 minutes, and there have been many people that have done that, because we've heard, well, I thought of that, and it's like, okay, go ahead and knock yourself out and try it, because it is very, very hard to make work correctly. The idea is simple. The execution is unbelievable. The amount of time we have in that boost controller tweaking and adjusting things is, you would never see that ahead of time going in until you actually run it and start looking at the data on it and realize how sensitive it is to certain things. And so it was iteration after iteration after iteration, tuning this, tweaking that, changing this, doing this. Oh, this is important, that's not. So, we've got 2 years in sorting out that controller to get the car down the racetrack to where boost comes on just the way we want it to and maintains it.
It's kind of hassle-free for the driver.
Yeah, once it's in, and dude, it's a no-brainer. You go up the starting line, you open the cylinders, you flip a toggle switch, and you mash the throttle, and away you go. That's all there is to it. And now that we know how to tune it, creating additional systems is not that hard, but the learning curve was huge. What we found was there was an enormous amount of effort that goes into making it launch correctly. We spent a year getting the car to launch correctly by playing around with the electronic boost controller and actually not just tuning it, but changing the programs in it. And there's an enormous amount that went into getting the car to leave and not do something funny like overboost or fall on its face.
This is our boost control unit that we've developed over a 10-year period. The person that developed it happens to be standing here.
Hi.
Rocket car.
We were using an industrial controller developed by some people I know in Texas anyway, and it allowed us to do some initial testing, but didn't have all the features and wasn't appropriate for what we needed to do in a race car. So we had this developed specifically for our needs with a number of very unique tuning characteristics and programs in it that are required for the car to run correctly, including the fact it has a built-in data acquisition system that records all the functions of our controller, as well as some additional analog inputs, which allows us to monitor the performance of the car on the track and then pull it up and examine it via Bluetooth. Our single system will full volumetrically around 1200 CFM, which is about enough on this engine for 900 horsepower on something with some more compression in it that's more mechanically efficient. I'm not sure, but I'm thinking you can get pretty close to 1,000 out of this.
It's kind of like a plenum. Under a carburetor you have a plenum. If the motor feeds off the plenum, well, we have a big tube with 80 psi, 100 psi of air, and depending on what the motor needs, the pressure drops into your boost level, 5 pounds, 10 pounds, whatever you're aiming for.
Simplistic schematic. Here are your tanks. They start out at 3,300 psi. They can be anywhere between, during a run, 33 and 300. We can run down to 300 and still maintain power. They go into that mechanical regulator. It comes out of that mechanical regulator in between 100 and 120 psi. Goes to the front of the car to that safety shutoff valve. There's a little pressure drop across the valve as there is in a mechanical system. Coming out of that valve, you're at about 80 to 100 psi. Then you go into that electronic butterfly valve, which we call the EPR for short, or electronic pressure regulator. This butterfly valve is opening and closing to maintain whatever your intake manifold target pressure is. If you tell it at 8 psi versus 10 or whatever, anyway, this will be moving around as a function of engine RPM or whatever to maintain intake pressure. So, again, you've got 80 to 100 coming in. For argument's sake, you'll have between 60 to 100 coming out of that. It's being ejected into that big 4-inch aluminum tube that you saw. There's a small high-speed jet. It's about a little over an inch in diameter, so you got high-pressure air coming flying out of that, pressurizing this intake. And the intake is, you're targeting, like in this car, anywhere between atmospheric and 11 psi gauge. So you've got a sensor over here reading what's going on in here, controlling this valve. So you've got this closed loop control system that's, again, continually moving this valve to try to maintain whatever you program this level to be.
Thank you. So again, the selling point is that
Go fast.
it's making more power.
You can literally you can outpower any other type of device. There's no magic in it, it's just the physics behind it. You talk to anybody with an engineering degree or works with turbos or blowers, and they will readily acknowledge and can calculate how much power it takes to run one of those, and this doesn't consume any power. And then also the inlet charge temperatures are super low due to the expanding air as opposed to compressing air, so there's just inherent physical advantages that you can't get from anything else. The inlet charge temperatures are dramatically lower than you will encounter with any other power adder, meaning it's less sensitive to pre-ignition and detonation, so this system seems to be very soft on parts and very easy to tune.
How often do you refill the cylinders?
Well, in the case of our Camaro, which makes about 800 horsepower, we use about 160 cubic feet of air per run, which is equivalent to what's in one of these tanks. And you can't completely scavenge a tank. You need to leave about 10% in it at the end to make sure that you're still maintaining full flow capability. So we run 2 tanks in this car. We bleed them down on each run just a little more than halfway. So we top the tanks after each run.
How do you fill the air cylinders?
Well, there are 4 discrete ways you can do it. The first would be taking your cylinders to a local scuba or compressed gas specialty shop and having them filled, which isn't terribly practical because to support a full weekend at the track you would need a large number of cylinders, which would be costly and bulky. The second way you could do it would be to take several cylinders like these that have been pre-pressurized to the track and fill by a cascade system. That's better. The third way you could do it is to take just a standard scuba type compressor, fill the tanks directly. Lastly, the preferable way is to have a scuba compressor with at least 2 cylinders, in an ideal world 4, and create a local cascade system such that you can fill many cylinders in a short period of time. As an example, this Bauer Oceana compressor will fill these the carbon fiber tanks, in about 40 minutes. If you use it and pressurize these cylinders ahead of time, you can fill each cylinder in about 5 minutes from empty. In fact, you could fill 2 cylinders at a time in that same 5-minute period. So it highlights why that is a preferred method of filling cylinders.
How much does a compressor system cost?
Well, what you're looking at here is what I would consider to be an idealized track support system. It uses a small scuba compressor, a Bauer unit, which is the Mercedes of scuba compressors, and it's rated for continuous operation when it's hooked to at least 2 cylinders. There are cheaper ways to do it. I mean, there are compressors out there for $3,000 brand new, but the Bauer unit will give you years and years of trouble-free service. So this particular unit, brand new, is about $6,000. However, we were wheeling and dealing, we got it for $4,500. These cylinders, brand new, I think are about $600 a piece. But again, wheeling and dealing, we've got them for $300. So the total setup you see here is about $7,000, and it's adequate for supporting multiple cars at a track continuously throughout a season.
But it's normal air, it's not pure oxygen or something?
Oh, no, because if you run high percentages of oxygen, your combustion temperatures go to the moon and you'll melt parts. And when we first looked at that, that was one of the thoughts I had. In the United States, the stuff is marketed as nitrox. It's up to 40% oxygen, juiced scuba. But the combustion temperatures are just, they go sky high with that. And I come back to, if you want to make more power with this, you just turn the boost up. I mean, literally, you go to the racetrack and it's silly. You want to go faster, you go tap, 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 enter, and then go out and make another run. The car, the best it ever ran, normally aspirated is like 1270. That was with a 456 gear in it. And you couldn't go to high boost with that gear in it because it would overspeed the engine. With 4 pounds of boost, I don't remember what gear we had in it, the car ran 1080 or something like that. It picks up about a quarter of a second for every pound of boost. So this car's run a best of 980 at 8 pounds of boost with a 370 gear in it.
So how many pounds of boost can you do?
I don't know. We haven't reached the limit on the dyno. We ran 10 and we had a little left. So I'm guessing on this engine, on a small engine, we could run a lot higher boost because it's the amount of air we're flowing is the limit, not the boost level. So a small engine, you can run a lot of boost. A bigger engine, not so much. So on this particular engine, it looks like 11 pounds of boost. What matters to an engine is not, typical people think of volumetric flow rate, right? 800 CFM Holley carburetor, 1000 whatever, right? And that's purely a function of the volume. We can really get off in the weeds with this, but that's a volumetric device. And if it's really cold outside, your car will make more power than it will when it's hot out, right? It's not flowing any more volumetrically because its engine just a pump. It's just the air is much denser. Is the temperature. Mm-hmm. And that's, again, one of the reasons this makes so much power is the air charge is super cold, so at very low levels of boost compared to what you're used to seeing, you're moving the same mass flow amount of air through. And the amount of fuel that you're combusting is related to the mass of air you're flowing, not the volume of air.
How is it getting cold?
It's because instead of compressing the air, when you compress air, it gets hot. There's the heat of compression as you're pumping energy into it. But when it gets hot, it gets thinner. The air is less dense. Well, in this case, the air is at 3,300 psi in the tank starting. And when you discharge it or throttle it down to 100 psi, there's a phenomenon commonly referred to as the Joule-Thomson effect, because that was the guys that discovered it 200 years ago or whatever. It's also constant enthalpy throttling, but the bottom line is when you throttle high pressure air to low pressure, you get a huge temperature drop with it. So that's the big kicker here, is when you go from 3,300 down to 100, the temperature out of that regulator before it comes through the line can be as low as 200 degrees below zero. We've measured as low as 140 degrees below zero Fahrenheit coming out of the regulator, and out of the ejector we've measured 80 below zero. Because the air is that cold doesn't mean the part's that cold, because there's heat transfer through the part, right? And so the part's chilling down, but because this is drag racing and is used for such a short period of time, nothing ever stabilizes the temperature. So yeah, you'll get a run and you'll open the trunk at the end of the run and the parts are sweating and water's pouring off them from humidity. But you haven't run it long enough where it's a giant ice ball or anything freezing the humidity here, or the aluminum components in the system aren't dropping to that temperature because they've got a thermal mass associated with them, and they're sucking heat out of the system. So, there is not a pat answer that it's this number. It just changes.
Will it be more test beds than this Camaro for drag racing use?
Yes,
to test?
we got the dual system, and then we'll probably put an LS motor in the Camaro and work on that for the new Camaro market.
There's a practical limit to what we're going to do with this car, because I don't know, 1,000 horsepower or so, 1,100. Should run high eights, and the car is certed 850.
Why not test on the methanol dragster or something that...
As manufacturers, we don't want to compete because our customers are the competitors, so we want to make sure they get high quality parts and stuff. Our marketing plan is to get tuners like Kenny Detweiler and people like Leonard at Auto Shop in Florida, like he was doing, that build motors, superchargers, turbochargers, and they will help with the customer getting started with compressed air supercharging.